Welcome! Today, we'll be tackling an interesting problem titled Minimum Number of Flips to Convert Binary Matrix to Zero Matrix. In this problem, we explore how to transform a binary matrix into a zero matrix by flipping cells strategically. Let's dive in and explore the intuition, approaches, and techniques to solve this challenge effectively. In this problem, you are given a binary matrix, where each cell contains either a 0 or a 1. Your task is to convert this matrix into a zero matrix, meaning all cells should contain the value 0. To achieve this, you can flip any cell in the matrix. For corner and edge cells, fewer neighbors are affected because some are outside the matrix boundaries. The objective is to determine the minimum number of flips needed to convert the matrix into a zero matrix. If it is not possible to achieve this transformation, you return -1. The input is a 2D binary matrix, and the output is an integer representing the required flips or -1 if it is impossible. However, flipping a cell has a unique effect. It not only changes the value of the selected cell but also flips the values of its four neighbors, those directly above, below, to the left, and to the right. Let's look at an example to understand the problem better. Suppose the input matrix is a 2x2 binary matrix, 0, 0, 0, 1. The goal is to transform this matrix into a zero matrix. To do so, we start by flipping the bottom right cell at position 1, 1. This changes the value of that cell and its neighbors, resulting in the matrix 0, 1, 1, 0. Next, we flip the top right cell, which is at position 0, 1. This operation again changes the selected cell and its neighbors, leading to the matrix 1, 0, 0, 0. At this point, the matrix is almost a zero matrix, except for the top left cell. To complete the transformation, we flip the top left cell at position 0, 0. This operation changes the value of the selected cell and its neighbors, resulting in the matrix 0, 0, 0, 0, which is now a zero matrix. In this example, it took a total of 3 flips to achieve the desired transformation. Another example demonstrates a simpler case where the input matrix is 0. Since it is already a zero matrix, no flips are needed, and the output is 0. These examples illustrate how the flipping operations work and how the minimum number of steps is calculated. In another example, consider a 3x3 matrix, 1, 1, 1, 1, 0, 1, 1, 1, 1. Here, it is impossible to transform the matrix into a zero matrix using the flipping rules. This is because certain configurations of the matrix cannot be resolved into all zeros, no matter how the flips are applied. In such cases, the output is -1. These scenarios highlight the importance of determining whether a solution exists before attempting to compute the number of flips. Some configurations are solvable, while others, like this one, are not. The constraints of the problem ensure that the matrix dimensions are small, with m and n ranging between 1 and 3. This means the matrix can have at most 9 cells. For edge cases, if the matrix is already a zero matrix, the output is 0. For a single-cell matrix, flipping the single cell toggles its value, resulting in either 0 or 1. Since the matrix is small, we can efficiently explore all possible combinations of flips using techniques like bit masking or breadth-first search, BFS. BFS is particularly useful for finding the minimum number of steps, as each matrix state can be represented as a unique binary string or bit mask. By understanding how flips affect neighboring cells and using efficient algorithms, we can solve the problem systematically, even for the maximum-sized matrix. To solve this problem, we first considered 2 different approaches. The brute force approach involves trying every possible combination of flips for the cells in the matrix. For an MXN matrix, there are 2 m*n potential combinations of flips. For each of these combinations, we simulate the flipping process and check if the resulting matrix becomes a zero matrix. The steps include generating all subsets of cells to flip, simulating the flipping for each subset, and recording the minimum number of flips required to achieve the zero matrix. However, due to the exponential growth in the number of combinations, the time complexity of this approach is 2m*n*, m*n*, which is computationally infeasible for larger matrices. Because of this, we turn to a more optimized approach using breadth-first search, or BFS. The intuition here is to treat each matrix state as a node in a graph, where flipping a cell transitions the matrix to a new state. BFS can then be used to find the shortest path from the initial matrix state to the zero matrix, which represents the minimum number of flips. By representing the matrix as a flattened binary string, where each bit corresponds to a matrix cell, we can efficiently track and transition between states. The key to this approach is understanding that flipping a cell toggles not only that cell but also its valid neighbors up, down, left, and right. The ultimate goal is to reach the binary string that represents a zero matrix. Using BFS to solve the problem involves a few critical steps. First, the matrix is flattened into a binary string representation. Then, we use a queue to perform BFS, starting with the initial state of the matrix and a flip count of 0. For each state, we generate all possible next states by flipping each cell and its neighbors, adding these new states to the queue. To ensure we don't process the same state multiple times, we use a set to track visited states, which avoids redundant computation. In terms of complexity, the worst-case time complexity is O(m*n*n) due to the large number of potential states and transitions, while the space complexity is O(m*n) for storing visited states. To further optimize the approach, we can use bit masking. Instead of explicitly storing matrix states as strings or arrays, we represent each state as an integer, where each bit corresponds to a cell in the matrix. This significantly reduces memory usage and makes flipping operations more efficient. The steps for this approach are similar to BFS, but transitions are computed by directly manipulating bits in the integer representation. While the time complexity remains the same as BFS, the reduced memory overhead makes this technique more scalable for larger matrices. After evaluating these approaches, the BFS strategy emerges as the optimal solution for this problem. BFS ensures that we find the minimum number of flips needed to achieve the zero matrix by systematically exploring all possible states. While the brute force approach is simpler to implement, its exponential growth makes it impractical for larger inputs. BFS strikes a balance between optimality and performance, systematically finding the shortest path to the solution. Incorporating bit masking into BFS further optimizes memory usage and speeds up state transitions, though it does introduce additional complexity in implementation. The key trade-offs between these methods highlight the strengths of BFS with bit masking. It minimizes memory usage while still guaranteeing optimal results. Ultimately, this combination of BFS and bit masking offers the most efficient and practical solution, ensuring we achieve the zero matrix with minimal computational overhead while handling larger problem sizes effectively. In this problem, we need to transform a binary matrix into a zero matrix, where all elements are zero. To do this, we can flip cells, and flipping a cell not only toggles its value but also toggles the values of its adjacent neighbors, those directly above, below, to the left, and to the right. A brute force approach to solving this involves enumerating all possible combinations of flips. Since the matrix has m*n cells and each cell can either be flipped or not, there are two m*n potential flip combinations to consider, which can be represented as binary strings. Each bit in the binary string corresponds to a cell in the matrix, where a 1 means the cell is flipped and a 0 means it is not. Once we generate a combination, we simulate the flipping process by toggling the specified cells and their neighbors. After applying all the flips in the current combination, we check whether the resulting matrix is entirely zeros. The next step is to keep track of the minimum number of flips required to achieve the zero matrix. As we evaluate each combination, we count the flips used and update our minimum if the current combination successfully transforms the matrix into all zeros. If no combination results in a zero matrix, we return -1 or indicate that the transformation is impossible. However, this brute force method has significant drawbacks. First, the time complexity is exponential, O(2*m*n), because we must evaluate every possible combination. Additionally, simulating the flipping process for each combination adds further computational cost of O(m*n) per combination, as we must traverse the matrix and apply the flipping logic. Despite these inefficiencies, brute force ensures correctness by exploring all possibilities and serves as a baseline before moving to more optimized approaches. To implement this, we use a 2D array to represent the binary matrix, a binary string or bitmask to represent flip combinations, and a temporary matrix to simulate flips without altering the original input. To address the limitations of the brute force approach, we can explore optimizations. One such optimization is to prune infeasible combinations early. If a partial flip combination cannot possibly lead to a zero matrix, we can terminate it without further exploration. Another technique is memoization, where we store the results of previously tested states to avoid redundant calculations. This can significantly reduce the number of repeated operations. Additionally, we can reduce the search space by leveraging problem-specific properties, such as symmetries in the matrix, to eliminate equivalent flip combinations that would produce the same result. These optimizations help mitigate the exponential growth of the brute force approach, making the solution more practical for larger matrices. To illustrate these concepts, let's walk through an example. Consider the input matrix 1 0 0 1. First, we generate all possible flip combinations 0 0, no flips, 0 1, flip bottom right, 10, flip top left, and 11, flip both corners. For each combination, we simulate the flipping process. For example, with the combination 0 1, flipping the bottom right cell toggles the values of the cell itself and its neighbors 1 1 0 1 and 1 0, resulting in the matrix 0 1 1 0. We repeat this process for all combinations, checking the resulting matrix to see if it is entirely zeros. Among the combinations tested, the minimum number of flips required to achieve a zero matrix is 2. This example highlights how we systematically evaluate each possibility and track the minimum flips needed. To solve the problem, we start by importing the Deque class from the collections module, which will help us implement a breadth-first search later. Inside the solution class, the min-flips method begins by determining the dimensions of the binary matrix, M and N. The first helper function, matrix_to_mask, is designed to convert the binary matrix into a single integer representation called a bit mask. This is achieved by iterating over each cell of the matrix. If a cell contains a 1, we use bitwise or to set the corresponding bit in the bit mask. This transformation allows us to efficiently represent the matrix's state. Next, we define the flip function, which simulates flipping a specific cell and its neighbors. For each cell, we adjust its coordinates to include all valid neighbors within the matrix's bounds and toggle their bits using bitwise XOR. Finally, we calculate the starting mask, which represents the initial state of the matrix, and check if it's already 0. If it is, we can immediately return 0 since no flips are needed. If the initial state isn't 0, we proceed with a breadth-first search to find the minimum number of flips. We initialize a queue using Deque, where each element is a tuple containing the current mask and the number of flips taken so far. We also use a set called scene to track visited states, ensuring we don't revisit them. While the queue isn't empty, we dequeue the front element and iterate over all cells in the matrix. For each cell, we calculate the next possible mask by flipping it and its neighbors. If this new mask equals 0, we return the current step count plus 1, as we've successfully converted the matrix to all zeros. Otherwise, if the new mask hasn't been encountered yet, we add it to the scene set and enqueue it with an increment step count. If the queue is exhausted and no solution is found, we return -1, indicating that it's impossible to convert the matrix to a zero matrix. Here, we start by defining the Java implementation for solving the problem. First, we define the min-flips method, which takes a 2D binary matrix as input. The dimensions of the matrix are stored in M and N. The next step is to convert the matrix into a single integer using a bitmask representation, which is achieved by the helper method matrix_to_mask. This allows us to treat the problem as a state space where each state is represented by a unique integer. If the initial state, represented by startMask, is already 0, we return 0 as no flips are needed. Otherwise, we initialize a breadth-first search, BFS, to explore all possible states. We use a queue to manage the states to explore, and a set to keep track of visited states, ensuring we don't revisit the same configuration. The BFS begins by adding the starting state and marking it as seen. The main BFS loop dequeues the current state, examines its bitmask, and iterates over all possible flips for each cell in the matrix. For each flip, the flip method calculates the resulting bitmask. If this new state is 0, we return the number of steps taken so far plus 1, as we've successfully converted the matrix to all zeros. Now, if the resulting state after a flip isn't 0, we check if this state has been seen before. If it hasn't, we add it to the scene set to avoid revisiting it, and enqueue it along with the increment step count. This ensures that all valid states are explored in the shortest possible number of steps. If no solution is found after exhausting all possible states, the method returns -1, indicating that it's impossible to convert the matrix to all zeros. After the BFS logic, we define the matrix to mask method. This utility method generates the integer bit mask that represents the input matrix. It initializes a mask to 0 and iterates through each cell of the matrix. If a cell contains a 1, the corresponding bit in the mask is set using a bitwise OR operation. The position of the bit is determined by the row and column indices of the cell. This bit mask is what we use to represent the matrix's state during our BFS traversal. We then move on to the flip method, which performs the actual bit flipping operation for a given matrix cell. In the flip method, we employ a helper array called directions to define the relative positions of the target cell and its neighbors. This array allows us to calculate the effect of flipping the target cell itself, as well as its adjacent cells in up, down, left, and right directions. For each direction, we calculate the new row and column indices. If these indices are within the bounds of the matrix, we flip the corresponding bit in the mask using the XOR operator. This effectively toggles the bit at the specified position. Once all relevant bits are flipped, the resulting mask is returned. This method ensures that each flip operation correctly simulates the toggling of the chosen cell and its neighbors, which is the core operation for solving this problem. With these helper methods, the BFS systematically explores all possible configurations of the matrix, ensuring that the minimum number of flips is calculated when a solution exists. To solve this problem, we start with a simple 2x2 binary matrix. Our goal is to determine the minimum number of flips required to turn this matrix into a zero matrix. First, we convert the given matrix into a bit mask representation. By flattening the matrix row by row, we get the binary number 0B0110, which corresponds to the decimal value 6. This value is stored in start_mask. Next, we check the base case. If start_mask is already 0, the matrix is a zero matrix, and no flips are needed. In this case, since start_mask is 6, it's not 0, so we proceed with the algorithm. To systematically explore the possible states, we initialize a breadth-first search, BFS. The initial state, represented by 6, 0, where 6 is the current mask and 0 is the number of steps taken, is added to the queue. This marks the beginning of our search for the solution. In BFS, we also need to track the states we have already visited to avoid redundant processing. Here, we start by marking 6 as visited by adding it to the scene set. During the first BFS iteration, we dequeue the state 6, 0. This means the current mask is 6, and we've taken 0 steps so far. From here, we try flipping each cell in the matrix. Flipping cell 0, 0 affects itself and its neighbors, resulting in a new mask of 0B1011, or 11 in decimal. This state, along with the step count increment to 1, is added to the queue. Similarly, flipping cell 0, 1 leads to a new mask of 0B1000 or 8, which is also added to the queue. Flipping cell 1, 0 results in a mask of 0B0100 or 4, and flipping cell 1, 1 results in a mask of 0B0001 or 1. All these new states are added to the queue and marked as visited. In subsequent BFS iterations, we continue exploring these states, trying all possible flips. Eventually, we reach a state where the mask becomes 0, which means the matrix has been turned into a zero matrix. For this example, the minimum number of steps required is 2. In a simpler scenario, we consider a matrix that is already a zero matrix. Here, the input matrix is a 2x2 grid with all zeros. As before, we convert this matrix into a bit mask. Flattening the matrix row by row gives the binary number 0B0000, which corresponds to the decimal value 0. This is stored in start_mask. Next, we check the base case. Since start_mask is already 0, the matrix is already a zero matrix, and no flips are needed. Therefore, the result is 0, and the algorithm terminates immediately without needing to explore any states. The result for this example is straightforward. Since no flips were required to convert the matrix into a zero matrix, the output is 0. Now, let's look at another example with a slightly larger matrix. Here, we have a 1 by 3 binary matrix. The input matrix is 1, 0, 1. As always, the first step is to convert the matrix into a bit mask. Flattening the matrix gives us the binary number 0b101, which is equivalent to the decimal value 5. This value is stored in start_mask, and we can now proceed to explore the solution using BFS. To solve this case, we initialize BFS with the starting state, 5, 0, in the queue, where 5 is the current mask and 0 is the step count. We also track visited states by adding 5 to the scene set. In the first BFS iteration, we dequeue the state, 5, 0, and try flipping each cell in the matrix. Flipping cell 0, 0 results in the new mask 0b011, or 3. This state, along with an increment step count of 1, is added to the queue. Next, flipping cell 0, 1 gives the mask 0b111, or 7, which is also added to the queue. Finally, flipping cell 0, 2 results in the mask 0b100, or 4. These new states are now part of the BFS queue. In subsequent iterations, we continue exploring these states, flipping cells and tracking visited masks. Eventually, we reach a state where the mask becomes 0. For this example, it takes 3 steps to convert the matrix into a 0 matrix. Thus, the output is 3. Here, we break down the time complexity of our solution. First, we convert the binary matrix into a bit mask using the matrix_to_mask function. This step involves iterating through all the elements of the matrix, which takes m*n time, where m is the number of rows and n is the number of columns. Next, we employ a breadth-first search, or BFS, to explore all possible states of the matrix. Since the matrix is represented as a bit mask, the total number of possible states is 2*m*n, where each state represents a unique configuration of the matrix. For each state, the algorithm considers flipping every cell in the matrix, which involves m*n time per state. In the worst-case scenario, all 2*m*n states may need to be visited, resulting in an overall time complexity of 2*m*n for the BFS process. Together, these steps outline how the time complexity is derived. In summary, the overall time complexity of the solution is m*n plus 2*m*n*. The first term, m*n, accounts for the matrix to bitmask conversion, which is relatively negligible when compared to the second term. The dominant term, 2*m*n*, arises from the BFS exploration, which governs the overall complexity. Now, turning to space complexity, the storage requirements are determined by the BFS queue in the scene set. The BFS queue holds the states, represented as bit masks, and their associated step counts. In the worst case, the queue could store all possible states, requiring 2*m*n space. Similarly, the scene set tracks visited states to avoid redundant processing, which also requires 2*m*n space in the worst case. Additionally, we consider the auxiliary space used during operations. For example, the flip function performs bitwise operations, which only need a small number of variables and therefore require 1 extra space. Similarly, the matrix_to_mask function also operates with 1 additional space. Combining these factors, the overall space complexity of the algorithm is 2*m*n, primarily driven by the BFS queue in the scene set. When analyzing the best, average, and worst cases, the best case occurs if the initial matrix is already a 0 matrix. Here, the algorithm terminates immediately after matrix-to-mask conversion, resulting in a time complexity of m*n. In the average case, the algorithm explores some subset of the state space before finding the solution, making the time complexity proportional to the number of states visited. In the worst case, all possible states are explored, leading to the full complexity of 2*m*n*. When comparing this approach to brute force, a brute force solution would involve examining all possible subsets of cells to flip, which corresponds to 2*m*n subsets. For each subset, flipping the cells and verifying if the matrix becomes 0 would take m*n time. This results in a time complexity of O, 2 caret, m asterisk n, asterisk m asterisk n, the same as BFS. However, the BFS approach avoids redundant calculations by using the scene set to track visited states, making it significantly more efficient in practice. From a mathematical perspective, the matrix has m rows and n columns, resulting in m asterisk n cells. Representing the matrix as a bit mask gives us 2 caret, m asterisk n, possible states. BFS ensures each state is explored only once, and for each state, it examines all m asterisk n neighbors, yielding the total time complexity of O, 2 caret, m asterisk n, asterisk m asterisk n. The space complexity remains O, 2 caret, m asterisk n, due to the BFS queue and scene set. Thus, BFS is an optimal approach within the constraints of exploring all possible flips to find the shortest sequence. Let's start by discussing some common mistakes that can trip you up when solving this problem. One frequent issue is ignoring edge cases. For instance, scenarios like empty matrices, matrices with only one row or column, or cells at the edges that interact with fewer neighbors are often overlooked. These situations might seem rare, but they can cause runtime errors or incorrect results if your code assumes a uniform neighbor count or matrix dimensions. Another mistake is relying on an inefficient brute force approach where all possible flip combinations are tried, especially for large matrices. This leads to exponential time complexity, which is impractical as the input size grows. Lastly, incorrect flip propagation is another common pitfall. If you fail to propagate flips correctly to all affected neighbors, or if multiple flips are applied to the same cell without accounting for their combined effect, the matrix state can become invalid, resulting in incorrect solutions. Another mistake to watch out for is misunderstanding the problem statement. This can happen if you misinterpret the flipping rules, such as thinking you only need to flip the selected cell rather than both the cell and its neighbors. Such misunderstandings can lead to entirely wrong logic and flawed implementations. Additionally, overcomplicating the solution is a common issue. For example, introducing unnecessary data structures or using a complex recursive approach when a simpler iterative or greedy solution would suffice. This not only adds complexity but also increases the likelihood of bugs, making the solution harder to debug and maintain. It's important to keep your implementation as straightforward as possible while meeting the problem's requirements. Now, let's shift our focus to some key insights for interviews. Matrix problems often require analyzing neighbors, cells up, down, left, and right. Being able to efficiently access and modify these neighbors is a critical skill. You should also understand the concept of state flipping and how it propagates through the matrix, as this is central to solving many related problems. When approaching this problem, start by considering a brute force solution to fully understand its mechanics. Then, look for constraints, like sparse matrices or smaller dimensions, that might allow you to optimize using techniques such as greedy algorithms, BFS, or even bit masking. Remember to communicate your trade-offs clearly during interviews. For instance, explain why you might choose a brute force method initially for clarity, even though it's slower, before transitioning to a more efficient approach. Lastly, always highlight your testing strategy, describe how you would validate edge cases and extreme scenarios to show thoroughness and attention to detail. To broaden your understanding, it's helpful to explore related problems. For instance, LeetCode 289, The Game of Life, involves simulating matrix evolution based on neighbor states, which is conceptually similar to this problem. LeetCode 130, Surrounded Regions, deals with modifying matrix regions based on connectivity, while LeetCode 73, Set Matrix Zeros, requires propagating state changes across rows and columns. Finally, LeetCode 994, Rotting Oranges, uses BFS to simulate the propagation of a state within a grid. These problems introduce various techniques that can deepen your problem-solving skills. In terms of alternative approaches, you might consider a greedy method, where you identify patterns in the matrix to strategically minimize the number of flips. This approach is faster but requires a strong understanding of the problem structure. BFS or DFS is another option, treating the matrix as a graph to propagate flips. While effective for connectivity problems, it can be memory-intensive for larger matrices. Finally, let's discuss bit masking as an alternative approach. This technique involves representing the matrix as a bit mask, which allows for compact storage and highly efficient state manipulation. For example, each bit in an integer could represent the state of a cell, and flipping operations can be performed using bitwise operators. This approach is particularly useful for small matrices, where the exponential complexity of exploring all states is manageable. However, for larger dimensions, the number of possible states grows too quickly, making bit masking less practical. Despite this limitation, it remains a powerful tool for solving many matrix-based problems, especially when the input size is constrained. Great job following along. In summary, we explored how to solve the minimum number of flips to convert binary matrix to zero matrix problem. We discussed a brute force approach and highlighted areas for optimization. Remember, practicing such problems enhances both your problem-solving skills and your algorithmic thinking. Don't forget to like, share, and subscribe for more videos like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!